Any questions? We got 1 minute left. Bridget, questions?
Are you still trying to get their claws? Yeah, you look so bad. You guys are cheating.
Okay, guys, any questions? I'm sure someone's got a question. Is this thing on? Hello? Hello? Seems like after a weekend of looking over the material, there should be questions.
Are we going to go over carbon NMR today, or is that?
Once we get back to NMR, we will. All right, the first thing we need to do is finish up ozonolysis. Let's get started. A variety of sheets. Alkene reactions. We're down here we saw alkene. This is just generic alkene, happens to be cyclic. Oxygen tetroxide followed by a magic step. What does that do? Diol. Syn addition. A particular compound, you have 2 enantiomers. Yeah, you can also do this with carbon-4, but you got to keep it mild, right? We also saw that diols can be cleaved with pyridoxalic acid or sodium pyruvate. Basically, the 2 carbons become carbonyls, and you can cleave the 2 carbons. So if you did this, you would get this. Of course, because it's cyclic, you only get 1 molecule. If it was not cyclic, you get 2 carbonyls. You can also do the cleavage directly. And here's where we're going to start. We mentioned last time. Take an alkene ozonolysis using ozone, followed by a magic step. You get the same outcome. 2 carbons are cleaved, and each carbon becomes carbonyl. Let's look at this reaction. We actually have 3 sheets. Purple outline, I'm really not going by it. It's for your own benefit, okay? Just for organization. We'll look at a few little miscellaneous things. Most of this is in the handwritten. So we finished up here. Analysis. So here we go. Oxidative cleavage of alkenes in 1 step. Ozone. Take this alkene, ozone, magic step, you cleave it into these 2 compounds. Basically, in terms of producing the product, before we do mechanism, this gets cleaved, each carbon becomes carbonyl. So this becomes carbonyl, there is an H there, so that's it. Basically, under my hand becomes oxygen, okay? And that's the compound on the right. Under my hand becomes oxygen. And that's this compound. Mechanism. First off, ozone. Ozone typically in lab is generated by an ozone generator. Little structure of ozone, you cannot draw it without 2 charges. It's net neutral. Here we can do a resonance structure, move these electrons over. This, not a great resonance structure because this oxygen does not have an octet. In organic 1, we said that was a no-no. You can work with any resonance structure. I chose to do this, although I know it's a no-no. We could do it from here. In fact, I'll do it from here. This is an alkene with two substituents on this end, one substituent there, H. Basically, we could do it from here. Electrons attack oxygen. These electrons get pushed to this oxygen, which needs electrons. And then something has to come here that, because this left, well, this can come here. These three arrows give this. Or you could do resonance structure first, and then just do two arrows. It is a concerted addition. Because it's concerted, your groups do not have a chance to rotate or anything. And if we label this as 1, 2, 3, this would still be 1, 2, 3. 2 and 3 are trans. They're still going to be trans. They don't have any time to change. What does this give? This gives bond to oxygen, bond to oxygen. It gives this structure here. This is called a molozonide. It's got 3 oxygens bonded together. What does malo mean? that's MO, but malo in Spanish? Bad. It's a bad ozonide. I don't know why it's MO. It's not stable. This molozonide will break down by this arrow movement. You can start with any place here. Electrons move down. That's going to form double bond there. These get kicked off. They actually move up here to make double bond. These electrons move on to oxygen. What does that give?
2 carbons.
You're breaking the carbon-carbon bond. You give 2 carbonyls. When that moves on to oxygen, that's a minus now. 3 lone pairs. That's a carbonyl. This is called a carbonyl oxide because it's a very odd-looking carbonyl with another oxygen on it. So this thing spontaneously breaks apart into these 2. And we're not over. We're not done yet. This will then react. The carbonyl oxide will then react with a carbonyl compound, which happens to be right here, generated from this. We've got a dipole here. The nucleophile adds to carbonyl. By the way, in the second half of this course, we'll be adding lots of nucleophiles to carbonyls. Electrons here, electrons up. That's going to give the structure here. Which bond did we just make? We just made that bond right there. Basically, electrons to the carbonyl, electrons up, or onto the oxygen. That becomes minus. At this point, this will add to this carbon and push these electrons up because that oxygen wants to become neutral. And all of that, if you keep track of it, gives this. And this is called just an ozonide. Not a bad ozonide, but just an ozonide. It is stable. It can be isolated. It is a peroxide. It still does have 2 oxygens bonded, but it doesn't have 3. It no longer has 3 oxygens bonded to each other. This is stable. It can be isolated. It tends to be a little explosive. Peroxides tend to be explosive if they're pure. From here, we can react it with either zinc or dimethyl sulfide. We're going to call this magic. And I'm not going to give you a mechanism at all for this. This ends up giving your 2 final products. 3 oxygens there, 2 oxygens here. The other oxygen comes out as zinc oxide or dimethyl sulfoxide. So that's magic. Understanding the molozonide, the chemistry here. There's a couple of mechanisms in the workbook that sort of address this feature here, or this part of the mechanism. It's a little bit convoluted, a little bit long. Arrow movement, though, is pretty straightforward if you just follow the arrow movement that's shown there. Okay. One of the top 10 reactions in organic chemistry. Cleaving an alkene to 2-carbonyl compounds using the ozonolysis. Overall, it's called an ozonolysis reaction. Starts at ozone followed by a magic step. There's about 20 or 30 reactions that are top 10 reactions in organic chemistry. Grignard reaction, one of the top 10 reactions in organic chemistry. Making Grignards. Important thing here is aldehydes survive. Okay? Ultimately, what do we do? We cleave the alkene. On the right side, the carbonyl has 2 methyls. It'll be this. On the left side, the carbonyl has what? 1 ethyl and one H. So the left side is going to become an aldehyde, and the aldehyde will survive. Now we'll do this with another reagent, and we'll say that the aldehyde does not survive with the other reagent. Okay, predict product. You guys on my left predict product for the first ozonolysis. You guys on my right predict product for the second. And then we also need to be able to go backwards. What starting material would give those 2 products by an ozonolysis reaction? Does everybody do that? The first one, guys, we get these 2 aldehydes. One aldehyde has a succinyl benzaldehyde, the other aldehyde has a methyl. How's that look? Basically, what do? We cleave this. Each carbon becomes carbonyl. You can draw it however you want. I just do it with the carbonyls up.
I noticed none of these are on a texture substituted alkene for a reason.
Do what?
None of these are done on a texture substituted alkene for a reason.
I'm not sure if that's a reason or not. I'd have to think. You have to be careful. Does ozonolysis work on a tetrasubstituted alkene? I think it does. So I don't know if I just didn't do a tetrasubstituted by chance or on purpose. I think the Wittig reaction during test 4 doesn't work with tetrasubstituted, but I think this does. Basically, if there was, you just make 2 ketones. Okay. How about this here? We cleave this, carbonyl, carbonyl. I'll sort of draw it like it's drawn. Boop, boop, boop. That becomes carbonyl, yeah. Boop, boop. This carbon becomes carbonyl. And what's on this carbon? Yeah. That's strictly correct. But I like to draw in the hydrogen on my aldehyde. So it gives that ketone aldehyde. But they're still connected. What product, what would give these 2 products by an ozonolysis? Well, first off, what functional group is this going to be mainly? Alkene. Alkenes undergo ozonolysis to give 2 carbonyls. What's it going to be? If you think about it, that carbon and that carbon are going to be connected together as a what? As an alkene. So basically, here's your alkene. Carbon over here is going to have what? Two what on it?
Two apples.
Two ethyls. And the carbon over here is going to have what? A phenyl. Does this have stereoisomer possibilities?
No.
Is that stereogenic? No. So it doesn't matter how you draw it. Even if it did, would it matter?
No.
Actually, it does not matter. For example, this is trans, right? The cis alkene would give the same outcome. Okay? Here you go. You cleave this, that becomes carbonyl, this becomes carbonyl. There you go. That would be the alkene. So you need to be able to go both ways on. Okay? There's another reagent that will do this, and guess what it is? Remember that reagent where we had to do mild? KMNO4 mild, what does that do to an alkene? Cis-diol. KMNO4 harsh, what does that do to an alkene? It actually cleaves it and gives you the same thing as ozonolysis, with one exception. Aldehydes do not survive KMNO4. If you take this here, you would get ketone, dimethyl ketone, you know, it's acetone, and you'd also get the methylaldehyde, ozonolysis. KMNO4 with heat and usually like acidic conditions, which makes KMNO4 more stronger oxidant. You get the same two at the beginning, as shown there, but do aldehydes survive with KMNO4? No, just like if you react this with KMNO4, what do you get? Well, first you get what? The aldehyde, but does it stop there with KMNO4? No. We learned at the big three, take it all the way. That is, an aldehyde reacts further with KMNO4 and gives what? Carboxylic acid, just like I showed here. That's not going to survive. It will get further oxidized by the big three to the acid. So the outcome here would actually be the acid and the ketone. Aldehydes don't survive KMNO4. Do ozonolysis, the aldehyde will survive. If you work it up with zinc or dimethyl sulfide. Now you can work up ozone. The magic step of ozonolysis can be an oxidant. If it's an oxidant, then your aldehydes won't survive. But zinc or dimethyl sulfide, they will. Some books show a third type of magic step, and aldehydes don't survive that step. Okay. Here's just a procedure for how you do ozonolysis up here. One thing about ozonolysis, the solution will turn blue. It's done at -78. Ozonolysis, this basically means adding ozone is continued until the distinctive blue color of excess ozone is first observed. You can read this, how they did that reaction. By the way, this is the ozonolysis product we just covered. They're going on and doing a separate next step. This next step is an aldol reaction, which we'll cover during test 4. Look at a couple other applications. Here's a synthesis of Zoloft. Right here. And going from 28 to 29, they're combining two steps, B and C. I've shown the B product here. And then when they do C, they get that. But the B product is, what's happening when they go from this to this? Don't look at your reagent B. What's happening here? The chemistry's right here. It looks like they're kind of cleaving this carbon-carbon bond, and the carbon is becoming what? Carboxylic acid. Okay? It's an alkene cleavage with the carbon here becoming a carboxylic acid. What reagent would do that that we just covered? KMNO4. Or you could do ozonolysis and then a next step where you react it with maybe the Tollens reagent, kind of convert the aldehyde to the acid. That's what they're doing here. What reagent did they use? B. They're using KMNO4, they're actually using sodium periodate. T-butanol, I can't see what that is. Room temperature?
Yeah.
They're sort of doing a mix of oxidants. That's what they're getting. Then C is dimethyl sulfate, potassium carbonate. That looks like what you did in lab last week, yeah? Except you didn't use acetone, you used acetonitrile. They're removing a proton here to make the carboxylate, and then they're putting in dimethyl sulfate. And they're doing an SN2, and that's how they get make it an ester. So it becomes a O-methyl ester. So there's an example of an alkene cleavage. It looks like the other carbon would have, they just sort of purified that out. They didn't want the other carbon fragment. In organic 1, I gave you the alkene puzzle. Here's the alkene puzzle again. Except this time, I have not given you the answers to the 3 reactions that we did not cover in organic 1. For example, the one here that says 18, should have gave you the organic 1, I gave you the answer, but here I do not. What is that? Ozonolysis followed by dimethyl sulfide. I think the ones I starred were the 3 oxidative reactions. Okay, that's alkene oxidation. By the way, you wouldn't think that ozone is in the body, but some recent research suggests that ozone is what may lead to atherosclerosis in the body. How might that happen? Research suggests that ozone reacts with cholesterol in the body, and this alkene here gets oxidatively cleaved to the 2 carbonyls. And then from there, some additional chemistry can take place. Aldol, which is test 4. And these type of products actually is what causes the atherosclerosis. Question?
What was the, what was the word that you said we would call that in the body?
Atherosclerosis.
What's that?
Clogging of the arteries.
Oh, okay.
Plaque in the arteries. Heart attack. Stuff like that. High cholesterol doesn't help. That type of stuff. This may be a mechanism that leads to that with ozonolysis of cholesterol in the body. Did you know you had ozone in the body? Apparently there's a wee little bit, and this could be happening to cholesterol. And then these things down here are like precipitating in the arteries and stuff, and clogging up the arteries. So, application of ozonolysis. Before I saw that, I never thought ozone was really in the bubble. And on the back, there's a little discussion of that. Okay. Let's do a little multi-step synthesis. Hopefully you've been working on these. Any particular questions? Any particular one you want to do? Which one? Dita? Which one? This one here? Yeah. Okay, synthesize this compound starting with bromobenzene. Main functional group is carboxylic acid. How do you synthesize carboxylic acid? Alcohol. With alcohol? So if you get an alcohol, you can make the acid? Okay. We actually just saw another way. You could cleave an alkene, and if there was an H on one of the carbons of the alkene, it would become aldehyde, and that could be converted to acid. Problem with the alkene, although they use it in Zoloft, usually when you do synthesis, you make the compounds larger and larger and larger. Think about it, the alkene cleavage takes a large molecule and makes it two smaller fragments. So it's not usually good for synthesis. Usually you want to build your molecule up. One of the best, most common ways of making carboxylic acids that you know right now is oxidation of an alcohol. Primary or secondary? Primary. Okay, we eventually need to go back to that. But let's just go back one step. That is, how would you make that there? Take it back to what? This primary alcohol. If you had that, what would you react with to get that? KMNO4, what else? Chromium trioxide, acetic acid, or something, just to give you a variety. Okay, one of the big three. All the way to the carboxylic acid. Intermediate being the aldehyde. Okay, job's done. Now we just need to synthesize this. How do you want to synthesize that? Why epoxide? Carbon. So nucleophile? Can you make that a nucleophile?
Yeah, the starting reagent. Using magnesium, the starting reagent.
I could go back to this epoxide plus what?
Magnesium and the starting reagent.
Jordan, do you have magnesium in there?
If I had these two, Diction? If I had these two, would these react to give that? We would need what at the end after we reacted? We need a water workup, something to supply that H. Why are you going to make this? What do you react bromobenzene with? Magnesium and like dialphyl ether, common solvent for Grignard. Make the Grignard, react it with this. This is essentially, isn't that essentially this? These electrons add here, kick that off. That gives that, and then work up with water. Put the proton on. It's pretty straightforward. That wasn't many steps, was it?
So for the workup with the water to make the oxygen.
Yeah, some proton
Did you
source.
say like HCl trace or something like that?
Yeah, you can work it up with acid. Acid will certainly supply the proton. Water will also supply it in practice. Yeah, a lot of times you may add acid. Just got to be careful. If you add acid and you start heating on it, you might do some reaction with your product. So mile, or one equivalent, or trace, or something. Okay, there you go. How about this one here? How would you make that? I'll let you work on that on your own. Okay, please be working on these. There's just another one. Let's look at NMR, I believe. Any questions while we're getting NMR up? Okay, there was one last proton to do. We'll look at that another time, maybe. But right now, I'd like to move on to carbon NMR. Okay, we mentioned carbon NMR along the way as we were introducing proton NMR. We do carbon NMR, we actually do it on carbon-13 because it has a net spin of 1/2. Carbon-12, which was the most abundant isotope, doesn't have a net spin. So you can't do NMR on carbon-12. Carbon-13 is only 1% of carbon, okay? 1% of the carbons in your body are C13, 1% of the carbons in an NMR tube are C13. Because only 1% of your sample is NMR active, carbon NMR is much less sensitive than proton NMR. Thus, when you do carbon NMR, it takes a much longer time. Proton takes usually you do 16 scans. By the way, IR, how many scans does usually run? Yeah, I noticed that on Friday. It's usually 4. Stevens' method should be 4. 4 to 8. Proton 16 is just common. Multiples of 16 are common in proton NMR. Carbon NMR, thousands of scans. Okay? Instead of a couple of minutes, usually several hours. A lot of times you even run this spectrum overnight. Okay, so like 12 hours. We'll take a look at different scans a little bit later. Key info obtained, just like proton, you get the number of non-equivalent carbons. Okay? Now we've already done that. For example here, how many different carbons? 3 different carbons, so you get 3 different signals. Same thing as we did with proton, except we're focusing on carbon. Now, one thing we can say about these signals. Typically, the modern day carbon spectrum, all the signals are singlets. That is, we actually remove the coupling. You do get coupling, but we remove that by a special technique. We simplify the spectrum. So, you might hear someone say you would get 3 singlets here. 3, okay? When you have no coupling and everything is singlets, that's called a proton decoupled spectrum. All peaks are singlets. If coupling is kept, you do get splitting. And in carbon NMR, it's the H's that split. Okay? Just like in proton NMR, the H is split. In carbon NMR, the H is split. And what splits is the nearest H's. That's the same as proton. I mean, look at, okay, proton. What's this signal going to be in proton NMR for that CH3? Singlet, doublet? Why triplet, Kingsley? Because the nearest H's, that's not the nearest H's, that's the H's that we're getting the signal from. The nearest H's is right here. How many are there? 2, n plus 1 is 3, triplet. The nearest H is split. Well, the same thing with carbon, the nearest H is split. So what is this going to be, this carbon? Quartet. Why would that be a quartet?
Because it's got 3 H's bonded to.
3 H's bonded to it, or is that the nearest ones? Yeah, the nearest H's are the ones bonded to it. So this carbon has 3 H's. 3 H's bonded, 3 plus 1 is 4. That'll be a quartet. What would that be? Triplet, triplet. 2 triplets in a quartet, if we keep the splitting. But we typically remove the splitting in practice, and it's just going to be 3 singlets. Question?
What's the purpose of removing this splitting?
It simplifies the spectrum. We'll look at some examples.
But don't you get good information?
Very, yes. We lose good information. But it's going to be good information for us. Okay? It works out, but you're right. You do potentially lose. Now, I will give you the splitting, because I'm very nice. I will give you the splitting, and that should be good information for you. We'll look at some examples of this. Okay. Now, of course, you also tell something about the chemical environment. That's just like protons. Chemical environment comes from the peak position. And a signal that is more to the left is more downfield. And so we would think, hey, something is deshielding the carbon. Okay. So everything is analogous to proton, except we're just focusing on the carbon. Miscellaneous information. Now, one thing that's not analogous to the proton is that in carbon we don't use integration. Integration doesn't work in carbon NMR. That is, in proton, the area under the signal corresponds to the number of H's. So in proton, that and that, this would be 1 H, and that might be 3 H, because it's 3 times area under the curve. But in carbon NMR, this could both be 1 carbon. And you would say, well, why are they both 1 carbon? This is 3 times larger. Well, it just doesn't correlate in carbon NMR. Why? Why is integration not reliable with carbon NMR? It's due to variable relaxation rates. Carbon NMR. What is a relaxation rate? Keep your place. Remember when we said what relaxation was way back over here? You can absorb the energy, flip to the beta state, or you can measure what comes back out. Energy is released as it falls back down, and we can measure what's released. And when it falls back down, what's that called? Yeah. But in carbon, different carbons relax or give off the energy at different rates. Now, why does that affect integration? Now, it doesn't have to affect it. The reason it affects us is, basically it's because of time. You know how you said sometimes you're running overnight? Well, that's doing fast scans. Fast scan, fast scan, fast scan, fast scan. Still you have to do it overnight. And if you do a fast scan, let's look at relaxation. Let's say here's a carbon, carbon 1, and it relaxes. That is, it gives off its energy like that. And this is going to be some time. And we're going to observe this energy release up until right here. Maybe that's 2 or 3 seconds. We put in the energy and then we sit back and measure for 2 to 3 seconds. That's C1. And then another carbon may relax slower. Okay? And if we only measure for 2 to 3 seconds, we get all of this signal. Do we get all of that signal? No. We don't get all the signal. Because it relaxed slower. We say, hey, I'm only going to measure 2 or 3 seconds because I'm already running overnight. If I measure for 20 seconds and get all the signal, and now your integration works, you'll have to run it for a week. So we typically don't observe that long between scans, and we lose the slow relaxing signal. So both of these may be one carbon, but this signal may be tall because we got all the signal. But here we only got a third of it, and it may be short. They're both one carbon, but we don't know that. All we know is like we got two signals, and we're like, well, this is 3 times as tall. You can't call that 3C and this 1C. Integration doesn't work because of the time thing. Okay. Importantly though, which carbons relax the fastest? Turns out that carbons with hydrogens on them relax faster. And that's what it says down there. Carbons without an H tend to relax slow.
Is there any difference between like a CH3 and a CH2? Does the
No,
CH2
not too much. Not too much.
It's minimal.
Minimal.
Okay.
But here's the take home. Carbons that don't have an H, the signals will tend to be short or weak. Because they relax slow, we don't pick up the entire signal that comes back out. And I'm going to call those later on short peaks. What does a short peak mean in terms of the carbon? Typically it means no H. Alright? So, try to go through that quickly, but there's a lot of little things like this in NMR that we just don't have time to go into. But that one I think is sort of important enough to understand relaxation rates, why integration doesn't work. Here's an example of scans. Here's a compound. This is from the research lab. This was 65 scans. Of course, carbon NMR is 0 to about 200. It's like 20 times the scale of proton. What you see is lots of noise. This is lots of noise here in the baseline. You see some signals here. Signal 1, 2. Are those signals? That's actually solvent. Okay. What about here? Is that a signal? Basically, when you got a lot of noise, you can't tell what's signal and what's noise. What's that right there? Is that a signal or is that noise? But if you run this 5,000 scans, your signal to noise ratio will improve. And you can get a spectrum that looks like this. So now your peaks are better resolved, and you can tell what peaks are versus what. Okay, better noise to signal ratio, signal to noise ratio. So you see that guy right there that's trying to be a signal, but you maybe can't tell? It actually is there. This one here at 60, you couldn't even see it after how many scans? After 65 scans, you couldn't even see it. It took 5,000 for it to show up. Okay. Let's look at examples of the splitting of this coupling. Singlets versus keeping the coupling. And the question was, aren't we losing information? Well, let's see here. Here's a diethyl phthalate, carbon NMR with the coupling kept. At the top here. First off, how many signals do we expect? Well, we got symmetry here. This is shown condensed, but it's 1, 2, 3, 4, 5, 6. I can't see their number. Why is that 1, 2, 3, 4? Why does that say 3 or 4? Oh, the last out there is 5 and 6. That's 5 and 6. Okay. 6 carbons. Oh, by the way, we forgot to look at peak position. Yeah. Sorry, got a little. We skipped the chemical environment. We need to go back here before we look at that example. peak position in carbon NMR is actually very analogous to proton NMR. So the things you've learned for proton, you're going to apply. The only difference is there's like a 20 times difference in scale. And you can actually use what's called the 20 times rule to get a peak position. For example, aromatic and proton. Where do we expect H's in aromatic region and proton? 7 to 8. Well, guess what? You can multiply that by 20 and get the corresponding region for the carbon that those H's are on. So 7 to 8 times 20 is what? 140, 160? Well, guess what? That's aromatic region for carbon. So use your 20 times rule. For example, let's do it with this guy here. Where would you expect this in the H NMR? Bromine is de-shielding approximately 3 to 4. And the H NMR, a little bit downfield, but still in the sp3CH region. Okay, where do you expect that in the carbon NMR?
68.
The corresponding carbon. Okay? Now, it's not going to give you exact. It's actually more like the 16 or 17 times rule. Because usually it gives you a little bit too much. So the 20 times rule is very general, gets you in the ballpark. But don't be surprised if it's a wee bit off. Okay? So you can look at these, but just use that. The one new thing, though, is your carbonyl. Carbonyl region is roughly about 200 ppm. Now this says 160 to 210. I would say rough start 200. Broaden that out, I would say 180 to 200. Now from 180 to 200, it can be greater than 200 and it can be less than 180. Basically, it's more downfield than aromatic. What about the 20 times rule? The only time you have a H on a carbonyl is aldehyde. What is this in proton?
It's pretty far in the tail, it's like
9 to 10, that's aldehyde region. So what's 20 times?
200 to 180.
180, 200, right? See how the 20 times rule works? Get you in the region. Okay, now that we did that, let's go back to this compound here. I've got it drawn out up there, it's condensed here. 6 signals. Let's look at it up here, it's easy to see up there. Aromatics, how many aromatic carbon signals do we expect?
2.
3. Expect 3. Okay? And this is the aromatic region. Let me pull this down. I'll move it back up. Splitting. These are the 3 here. 1, 2, and 3. That's the same as that, same as that, same as that. What is this going to be if we kept splitting? Doublet. What is that if we kept splitting? And what is that if we kept splitting? Only H is on carbon split. Yes, there is a neighboring H, but there's no H on the carbon, and that's going to be a singlet. It will be shorter also. Doublet, doublet, singlet. What do we expect from the carbonyl in terms of splitting? Singlet. What do you expect from this guy? Triplet. This guy. Quartet. That's if we had splitting. You got that written there? I'm going to raise it back up now. Okay. Aromatic region. Doublet, doublet, singlet. I see 2 doublets. Where's the singlet?
Obscured.
It's obscured by one of the doublets. What is this guy? At about, what is that, 170?
That's the carbonyl, or the ketones.
It's a carbonyl. Carbonyl region is down here, past the aromatic. Okay, what do we expect for the alkane region? Triplet quartet? Which one's more downfield? Triplet or the quartet? Triplet, because it's bonded to oxygen. Okay, there you go. So there's a carbon NMR with splitting. How do I know the singlet is there? Well, look below. Down below is the proton decoupled spectrum, where all the splitting is removed. Everything is singlets. You've still got the same number of signals. Total signals is what? 6? Still got your 6. 1, 2, 3, 4, 5, 6. Ah! Look at that little guy right there. Because we simplified the spectrum and removed the splitting, we're able to see other peaks. We simplified. And the question earlier, why do we do this? Because often in carbon NMR, you often get signals on top of each other. And if they're split, they're all going to be on top of each other. But if we remove the splitting, this can become maybe 2 signals. And we can see them. That's why we do it in carbon. And so that's it. Now, why is that one so much shorter than the others? How many carbons is these? That's 2C, that's 2C, and that's 2C. Because we got symmetry. But why are these so much taller than that one? Because one of the carbons doesn't have an H. And that signal relaxed very slowly, and our scan time, we didn't get hardly any of that signal. It went on for 20 minutes, and we just didn't measure it all. Okay, please look at the spectra that are next. Start assigning peaks, number of signals expected, etc.